chapter. Welcome once again to our next chapter in gas turbine. This is compressors and delivered by Professor Mos Kafaras, Afritech University of Aeronautical Sciences. Don't worry, these are not 2 hours. It is intended, my presentation is expected to be 2 hours, but we will take about 10 minutes. Yeah, it has to be in a simple and easy to deliver content that you can even understand. So we'll go straight. The compressor is one of the most important components of a gas turbine. The task of the compressor is to increase the pressure of the airstream. The process is accomplished by supplying mechanical energy to the compressor. The rotating blades exert aerodynamic forces on the airflow. In fact, the compressor is driven by the turbines. So the turbines exert mechanical energy on the compressor blades, which rotate and exert aerodynamic forces on the airflow. So the compressor section, the primary function of the compressor is to force air into the engine for supporting combustion and providing the air necessary to produce thrust. That is its main function. So you can breathe is to force air into the engine. Another secondary function, to supply bleed air to cool the hot section and heated air for anti-icing. So the compressor also does that. It supplies bleed air. We always call it compressor bleed air, and it is for cooling. Mostly it can even be tapped and it goes into the cabin for pressurization and air conditioning. So in addition, compressed bleed air is used for cabin pressurization, fuel system de-icing, air conditioning, pneumatic engine starting, auxiliary drive units, control boosters. So measuring compressor effectiveness. How do we measure the effectiveness of a compressor? We compare the static pressure of the compressor discharge with the static air pressure at the inlet. So how do we do that? If the discharge air pressure is 30 times greater than the inlet air pressure, that compressor has a pressure ratio of 30:1. You compare the discharge with the inlet. So in other words, if you find that the discharge air pressure of 15 times greater than the air inlet pressure, and that compressor pressure ratio is 15:1. We can see that one. We can see the fan. These are the compressor sections. 1, 2, 3, 4, 5, 6, 7, 8. We have the inlet pressure, 14.7 psi, and then we have the discharge pressure, 97 psi. So if you compare this, 97 divided by 14.7, you get something like 6.6:1 as the ratio. So there's a pressure rise. Types of compressors. We had earlier seen that this type of a compressor determines the design of the turbine, gas turbine engine. So the 2 types are centrifugal flow and the axial flow compressor. Centrifugal flow compressors consist of an impeller made from forged aluminum alloy. It has a fixed diffuser and then a compressor manifold. Pressure can be increased by arranging 2 single-phase compressors in a row. So for you to easily understand this, you can just say call it IDCM, meaning impeller, diffuser, compressor manifold. Isn't it that? IDCM, or you can call it IDM, and that's an acronym for impeller, made from forged aluminium, diffuser, fixed, and compressor manifold. A pressure may be increased by arranging two single phase compressors in a row. So when you get two single phase compressors, you arrange them in a row, you increase the pressure. I think we can see here the parts of the centrifugal. We see the impeller, it has these blades, then we see the diffuser, and then we see the compressor manifold. Yeah, in brief, we can now see it very clearly: compressor cooper ring, compressor shaft, impeller, compressor rear inducer, then we got the front bearing retainer nut. This is a centrifugal compressor. So derivative of single phase compressor was the double phase compressor, in that after the single phase compressor we had to get a double phase compressor. So single phase, we saw that it can be made to get high pressure by using two. Now here we use one. Major benefit of centrifugal compressor is large pressure ratio per stage and has a low cost of manufacture. The operating principle: the impeller is driven by the turbine and it revolves at high speed. The inlet guide vents direct airflow to the outer circumference on the compressor. Airflow is induced by high rotational speed of the impeller. This process builds up pressure and also discharges airflow from the impeller at high velocity in the diffuser section. Kinetic energy of high velocity air is converted to pressure energy in that low velocity high pressure airflow. So the diffuser also serves to straighten the flow and to change its direction to 90 degrees. Okay, in the diffuser section, kinetic energy of high velocity air is converted to pressure energy. So it loses the high velocity to be low velocity and it gains pressure. So a diffuser also does another thing of straightening the flow and change its direction to 90 degrees. Construction of features: the centrifugal compressors are mounted on ball or roller bearings. They are driven by turbine stages. The connecting shaft may be in two parts with self-aligning coupling. The discs are forged with vanes straight. Separate rotating guide vanes are attached to the front of the impeller. The diffuser assemblies are often part of the compressor case. We go to the axial. The axial flow compressor has two main elements: a rotor, a stator. The rotor has fixed blades. The rotor has fixed blades on a spindle. These blades impel air rearward in the same manner as the propeller because of their angle and airfoil contour. So, axial flow compressor process. We have a rotor turning at a high speed. and it takes in air at the compressor inlet. It impels it. Let's see, it's rotor and stator, and the rotor blade is fixed on a spindle. These blades impel air rearward. So the rotor turning at high speed takes in air at the compressor inlet, impels it through a series of stages. The action of the rotor increases compression of air at each stage and accelerates it rearward through several stages. Energy is transferred from the compressor to the air in the form of velocity energy. The starter blades act as diffusers at each stage, partially converting high velocity to pressure. Each consecutive pair of rotor and starter blades constitutes a pressure stage. Each consecutive pair of rotor and starter blades constitutes a pressure stage. Because the starter blades act as diffusers, they convert high velocity into low velocity, high pressure. The number of rows of blades or stages is determined by the amount of air and total pressure rise required. The greater the number of stages, the higher the compression ratio. Construction or design of an axial compressor. The starter has rows of blades. Yes. The stator has rows of blades or vanes dovetailed into split rings, which are in turn attached inside an enclosing case. The starter vanes project radially toward the rotor axis and fit closely on either side of each stage of the rotor. We're looking at the construction design. The starter has rows of blades or vanes which are dovetailed into split rings and they in turn attached. Where is my cursor? The starter vanes project radially outwards. The starter blades or vanes project radially outward toward the rotor axis and fit closer on either side of each stage of the rotor. The compressor case into which the starter vanes are fitted is horizontally divided into halves. That is, so we can see the rotor, which is has a rows of blades or vanes, and they are all dovetailed into split rings. We can see that. Then also see the shroud, then the starter, then the case. We saw that a combination of this rotor and the starter makes a compressor stage. Yes. We saw that somewhere, that the starter vanes project toward the rotor axis and fit closely. We saw that the number of rows of blades is something. Consecutive pair of rotor and starter blades constitutes a pressure stage. So that's something that we see here. This is a stage. So any other rotor, starter, that's a stage. Either the upper or lower halves may be removed for inspection or maintenance of rotor and starter blades. That's why it is divided into two. That's why we have the compressor case into which the starter vanes are fitted, horizontally divided into two halves. That's for easy inspection and maintenance. The function of the vanes or the blades. One is to receive air from the air inlet duct or from each preceding stage of the compressor and deliver it to the next stage or to the burners at a workable velocity and pressure. That's the role of the vanes or the blades. They receive inlet air from the duct, receive air from the duct or from the preceding stage of the compressor, and they deliver it to the next stage, or at the end of the compressor they give it to the burners at a workable velocity and pressure. They also control the direction of air to each rotor stage obtain maximum possible compressor blade efficiency. The rotor blades are usually preceded by an inlet guide vane assembly. They have an inlet guide vane assembly. So the guide vanes direct airflow into the first stage rotor blades. So we can see the diagrams, we can see the front compressor starter casing, the rear, the compressor rotor, compressor rear frame, the front compressor starter casing, the rear compressor starter casing. So the inlet guide vanes are curved steel vanes usually welded to steel inner and outer shrouds. The inlet guide vanes may be preceded by a protective inlet screen. At the discharge end of the compressor, the starter vanes are constructed to straighten the airflow to eliminate turbulence. That's at the last stage of the compressor. The starter vanes are constructed to straighten the airflow to eliminate turbulence. Yet inside they were directing it to the next stage, but here they at the discharge they direct it, they straighten the flow. The casings of axial flow compressors are made in a way to support the starter vanes and provide the outer wall of the axial path the air follows. Casings of axial flow compressors support the starter vanes and provide outer wall of the axial path the air follows. So the casing also provides a means for extracting compressor air for various purposes. As we saw that the air can be used we tap it as compressor bleed air. The starter vanes are usually made of steel with corrosion and erosion resistant qualities. They are shrouded or enclosed. The vanes are welded into shrouds, and the outer shroud is secured to the compressor housing inner wall by radial retaining screws. The rotor blades are made of stainless steel. They are commonly fitted into discs by either bulb type or factory type rods. So this is the bulb type A, then B is the factory. If you have ever seen the factory, you can see these things. Oh Jesus, my cursor. You can see these ones. This is like a factory. This is like a bulb. So the blades are then locked by means of screws. That is pinning or locking wires, pins or keys. The blades vary in length from entry to discharge because the annular working space. Rotor features drum type or disc type construction. The drum type rotor consists of rings that are flanked to fit one against the other, wherein the entire assembly can then be held together by through bolts. So drum type has rings that are flanged to fit one against the other, wherein the entire assembly can then be held together through bolts. So you can see that. See the airflow, the drum type compressor rotor. We go to the disc type rotor. It consists of a series of discs machined from aluminium forgings shrunk over a steel shaft. Series of discs. The other one has rings that are flanged, fit into one after another, then after they are bolted. These ones are a series of discs machined from aluminium forgings shrunk over a steel shaft with the rotor blades dovetailed into the disc rims. Now, advantages. So I hope you have gotten the difference between the drum type rotor, that is how the blades are, the rotor features, how the rotor blades are arranged, either by the drum type or the disc type. So the drum type is a rings flanged one with the other, semi-assembly is held together through bolts. The disc type, series of discs machined from aluminium forgings and shrunk over a steel shaft, with rotor blades outside into the disc rims. Advantages and disadvantages. Centrifugal advantages: high pressure rise per stage, good efficiency over a wide speed range, simplicity of manufacture, low cost, low power for starting. Axial has its advantage of having a high ram effect efficiency, high peak pressure, and a smaller frontal area. Centrifugal also has an advantage of low weight and damage tolerant. Disadvantages: centrifugal has a large frontal area and is limited to 2 stages. Yet we see here, Axial can have as many stages as possible. Disadvantages of Axial: compressed manufacture, relative high weight, and again it also has a high starting power and a low pressure rise per stage. Yet we saw in compressor that it has a high pressure rise per stage. So Axial is the opposite. It has a low pressure rise per stage and it has a high starting power. Centrifugal has a low starting power. So thank you for tuning into us. So we're gonna be welcoming to the next section of the gas turbine. This was quite a long time, but we have finished it. Thank you. Tune on to our YouTube channel and subscribe.